probability models. In this unit, we're going to examine the way of handling a situation where you might have two outcomes that could occur, and what's the probability of outcome 1 and outcome 2 occurring. Also, finding a way of calculating the probability when outcome 1 or outcome 2 occurs. Review some terminology from the video. A sample space is all the possible outcomes that can occur. So say a car is coming to an intersection. The car can either go straight, turn right, or turn left. Suppose that after observing traffic patterns for a long period of time, the information in this table is obtained. Let's just work with this for a bit. Defining a random variable, what we're going to say is, let's say the variable A is that the car goes straight at some intersection, and the variable B is that the car either goes right or left. There are two ways of calculating the probability of event B happening. So the probability that event B happens could be, well, what's the probability of going right plus the probability of going left. So the way you interpret this is looking at the information. The vehicle is either going to go right or left. And so the key word here, if in the problem you can fit in the word or, that means you're adding probabilities, like I'm doing right here. So the probability of event B occurring just by adding the probability that the vehicle is going to go right, which is 0.25, and adding that to the probability that the vehicle is going to go left, which is 0.15, then the probability of event B happening, which is the car either turns left or right, is 0.25 plus 0.15, which is 0.40. So the probability that the car will go right or left is 0.4 or 40%. Now, once again, keyword here is or. The car is going right or left, so I'm adding the probabilities. The other way to do this is using the compilmentary rule. So here's how that works. The probability that event A occurs, in other words, the car goes straight, is equal to the difference between the 1 minus the probability that event B occurs. Well, because we're working with decimals, so 0.40 is the same as 40%. I could also say, if I wanted to, the probability that event A occurring is equal to 100 minus 40%. Well, that would be, well, 100% actually minus 40%, that's 60%. So the probability that event A occurs is 60%. In other words, the probability that somebody's going to go straight is 60%. However, with our probability calculations, we're not actually going to work with percents with a percent sign. We're going to work with the decimal form of the percent. So that's going to be the probability that event A occurs is 1 minus the probability that event B occurs. Well, event B, we figured out in the first sort of step of this situation. The probability that event B occurs, where the car goes either right or left, is 0.40. So the probability that event A occurs is 1 minus 0.4, which is 0.6, or 60%. This is known as the compilmentary. So the probability models for human blood types takes a bit of explanation. So this table, 19.4, lists all the possible human blood types. And when they say ABO type, what we're talking about is the main type, the letter. Is it A, B, 0, O, or AB? And the RH factor is whether it's positive or negative. So ABO type A can either be Rh positive or Rh negative. All of the blood types have that possibility. So in this table, for example, blood type A, where the Rh factor is positive, has a probability in the American population of 0.357 or 35.7%. So 35.7% of the American population has blood type A positive. 0.063 or 6.3% of the American population has blood type A negative. If you add up the probabilities for all the possible blood types, it adds up to 1 exactly. So in their example, let's say 2 events. E is a randomly chosen person, and they have blood type A, and F to be the event that a person has blood type O. It's important to note that people can only have one blood type. So we're saying the random variable E will be a person that has type A, and they can either be A plus or A minus. The random variable F is a person who is either O plus or O minus. Well, I've already introduced this concept, the previous example, but this is where we have the probability that event E occurs. That's the probability that some randomly selected person will have blood type A. So blood type A means it can either be A plus or A minus. Notice the keyword or. That means you're going to add the probabilities. To add the probability that somebody is blood type A plus to the probability that somebody is blood type A minus, and the value you get, 0.420, is the probability that somebody is blood type A, either A plus or A minus, and we assign the random variable E to that situation. So the multiplication rule occurs when you have two events or two or more events, but in our situation, 2 events where both events are occurring. So in this case, we want to find out what is the probability of 2 randomly selected people from the US population, both being type A blood. Well, previous example, we found that the probability of someone having type A blood is 0.420. So we want to find out if person 1 and person 2 is type A blood. The keyword here is and. When you're dealing with the keyword and, you multiply the probabilities. So the probability that person 1 is type A blood is 0.420. The probability that person 2 is type A blood is 0.420. The probability that person 1 and person 2 are both type A is the product of 0.420 times 0.420, which is 0.1764. So like 18% chance that 2 randomly selected US residents will be both ABO type A blood. Okay, in the next example, you're asked to calculate the probability that at least one of the 2 people who were randomly chosen does not have type A blood. So here's the question. The outcome, at least one of the 2 people does not have type A blood. So what we've got to do is we look at the 4 different situations. So if I'm trying to calculate the probability that at least one of the two people is not type A, I'm going to calculate the probability of that occurring, 2, or 3, or 4. So I'm going to say, and this is in your notes, the probability, say, of event C occurring, where event C is the probability that at least one person is not type A. That's the probability that 2 is occurring, or 3 is occurring, or 4 is occurring. Well, how do we calculate these various things? The probability that event 2 occurs, that person 1 is type A and person 2 is not type A, is going to be an AND situation. So you're going to multiply the probability that the person 1 is type A by the probability that person 2 is not type A. The probability that person 1 is type A is 0.420. The probability that person 2 is not type A will be 1 minus 0.420. So I'm taking, first of all, the probability that person 1 is type A, 0.420, and multiplying that by the probability that person 2 is not type A. So using the complement rule, 1 minus 0.420. And that product is 0.2436. Next, I'm going to calculate the probability of event 3, which is that person 1 is not type A, but person 2 is type A. So the probability that person 1 is not type A, using the complement rule, is 1 minus 0.420. And since we got a keyword AND, I'm multiplying that by the probability that person 2 is type A, which is 0.420. And this is also equal to 0.2436. Now, event 4 is the probability that person 1 is not type A and person 2 is not type A. So that will be 1 minus 0.420 times 1 minus 0.420. And I obtain 0.3364. So if you recall, in the notes, we said let's define the probability of at least one of the two people not being type A as being assigned to the random variable C. So the probability of event C occurring is, well, that's the sum of these three things, the probability of 2, the probability of 3, and the probability of 4 occurring. So now I add them up. So that's going to be probability of event 2 occurring is 0.2436, or event 3 could occur, and that probability is also 0.2436, or event 4 could occur, so that's 0.3364 probability that event 4 could occur. Now I sum these up. So the probability that event C will occur is 0.8236. Now, in your notes, they talk about using the complement rule, where you can go, okay, the probability of event C occurring is 1 minus the probability of not C. So you go 1 minus 0.1764. Well, what was 0.1764? 0.1764 was the probability of event 1 occurring that both person 1 and person 2 are type A. Notice in that situation that there's nobody who's not type A. And so there's two ways to calculate that. I just want to illustrate the method that they did not demonstrate in the textbook. Suppose that you're playing cards, or you have a card deck. 52 cards on a card deck, 4 suits. 2 of the suits are red, 2 of the suits are black. So the 2 red suits are hearts and diamonds. The 2 black suits are spades, clubs. 52 cards total in the deck, so that means that there are 13 spades, 13 clubs, 13 hearts, 13 diamonds. Okay, so here's a question. What is the probability that with a well-shuffled deck of cards that 2 red cards will be drawn one after the other with replacement? So what that means is you draw the top card off a well-shuffled deck and you go, oh, it's red. You put that card back in the deck to replace it back on the deck. You shuffle the deck again, and then you draw the top card again, and you go, oh, it's red. That means that we're going to say this is probability of event A occurring. And event A will be the probability that the first card drawn is red, and so multiply the probability that the second card drawn is red. And this is with replacement. Well, what's the probability of event A occurring if event A is that you draw 2 red cards in a row with replacement? Well, there's 16 hearts and 16 diamonds, so that's 26 out of 52 that you're going to get a red card with your first card drawn, and it's going to be the same 26 out of 52 when you draw the second card. But the probability that you draw the first card and it's red is 26 out of 52, and the second card that it's red is 26 out of 52. It means you multiply those two probabilities together. Now, I'm going to do that on a calculator, and we all have calculators that do fractions. So I'm going to express, first of all, the probability of event A occurring as a fraction, and then I'm going to make it a decimal. Well, the probability of drawing 2 red cards in a row with replacement, so card 1 is red and card 2 is red, is a half times a half, which is a quarter. So the probability of event A occurring is 0.25. Let's look at a slightly more complicated example. Let's say that we're going to define event B as the probability of drawing a red card from a well-shuffled deck of 52 playing cards, but then you don't put that card back. So this is without replacement. And now you draw the next card, and it's also red. So in this case, what we're doing is we're going to determine the probability of drawing a red card from the deck, and then so times the probability of drawing another red card from the deck. But this is without replacement, which means you don't put the first card back. So now, to calculate this probability, well, the probability of drawing that first red card out of the deck, well, there's a total of 26 red cards, and there were 52 cards in the deck. But now you're going to draw another card, and this next card is going to be red. So what happened was the first card you drew out of the deck is red. That means there's only 25 red cards left. Also, there's only 51 cards in total left because you haven't put one of them back. So now we're going to calculate the probability of event B, which is you draw 2 red cards in a row. First, 1 red card and a second red card without replacing the first card. Let's calculate what this is. Now this one I am going to need to use a calculator for. Well, this works out to be 25 over 102 when you use your calculator to find the common, to multiply the two fractions together and then reduce them to lowest terms. You know, of course, you could have just done it as well by hand, but calculator is easier. And converting 25 over 102 to a decimal is 0.25. So there's a 24.5% chance that you are going to draw one red card sequentially after another red card from a well-shuffled deck without replacing the first card. Let's look at some more examples rolling dice. So suppose you have two die, and each die is a fair die. So each die has an equal probability of rolling any number. So what's the probability of rolling, I don't know, an 11? Well, okay, so the probability of rolling 11. Well, let's take a look at our sample space, which is in blue on this chart. There are two die, and each die can roll any number between 1 and 6. So what's the probability of rolling an 11? Well, looking at our sample space, there's two ways you can make 11. You can either roll a 5 and a 6 or a 6 and a 5. The probability of rolling an 11 then is the probability of rolling a 5 followed by a 6, which is actually 1 in 36, plus the probability of rolling a 6 followed by a 5, which is also 1 in 36, because you can get an 11 this way or that way. So you're going to add your probabilities. So the probability turns out to be 2 in 36, which reduces to 1 in 18. And then you convert that to a decimal. This works out to be 0.0556. Well, actually, it's around 5.6%, roughly. So not a high probability that someone would roll 11. What about the probability that somebody would roll a number with two dice that's less than or equal to 3? Well, what are those possibilities? Well, we're looking for numbers that are less than or equal to 3. So that means, well, n could be equal to 2 or 3. Well, what combos allow that to happen? We look at our sample space. You can get a double 1, a 1 and a 1, a 2 and a 1, or a 1 and a 2. So those are your three possibilities. So the probability that n will be less than or equal to 3 will be 1 over 36 plus 1 over 36 plus 1 over 36, which is equal to 3 over 36, which is equal to 1 over 12. So the probability that the sum of the two dice will be less than or equal to 3 is 0.0833, or 8.33%. Well, what's the probability that the sum of the two dice will be less than 6? So that means, okay, if the sum of the dice is less than 6, since can't have any fractions here, that means the sum of the dice has got to be 5 or less. Where's 5 here? There's a 5, there's a 5, 5, 5, and then a 4, a 4, a 4, a 3, a 3, and a 2. The probability then that two dice will have a sum less than 6, which means 2, 3, 4, or 5. Well, how many possibilities are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there are 10 possibilities. So the probability will be 10 over 36. Well, how did I get that? Well, I said that this is really the same. There are 10 possibilities, and each possibility has a 1 in 36 probability. So 10 times 1 is 10. So that's how I came up with that. So what does that reduce to? As the probability the sum is two dice can be less than 6 is 0.278, or 27.8%. Okay, let's look at blood types again. What is the probability that if 2 Americans are selected at random, that exactly one will have blood type ABOA plus? So there are 2 Americans, and we want to find out what is the probability that exactly one has blood type ABOA plus. American 1 could be A plus, and American 2 could be A plus. American 1 could be A plus, and American 2 not A plus. American 1 could be not A plus, but American 2 could be A plus, or both 1 and 2, both Americans could be both not A plus. But for there to be exactly one of them to have blood type ABO plus, that's possible if the first American is A plus and the second American is not A plus, or the first American is not A plus, but the second American is A plus. Okay, so how do we calculate the probability? Well, do it like this. The probability that exactly 1 is A plus would be equal to, well, the probability that 1 is A plus and 2 is not A plus. Okay, so I'm just going to multiply those probabilities together. So the probability A plus times the probability not A plus plus the probability not A plus times the probability A plus. You see, the way this works is American 1 could be A plus and American 2 not A plus. So you multiply those probabilities. Or, and this is the or situation here, or American 1 is not A plus. So there's an or, it's going to put a plus sign. So the probability that American 1 is not A plus times the probability that American 2 is A plus. So this combo is that first situation where those two probabilities are multiplied together. This combo is the probability that first American is not A plus multiplied by the probability that the second American is A plus, because American 1 is not A plus and American 2 is A plus. Well, what we are doing then, if I was to read it out, is we're saying that American 1 is type A plus and American 2 is not A plus. That gives us this first combo that was multiplied together. Or, so we put a plus sign, American 1 is not A plus, and so multiply American 2 is A plus. Well, now I'm going to get the numbers. So there's a 0.459 probability that exactly one of the two people would be blood type A plus, or 45.9%. Well, how does the frequency distribution look like when you roll 2 dice 100 times? What I've done is used the dice roller app, and I did 100 rolls. The gray is the expected outcome, the red's the real frequency. And you can see that it's pretty close to being close to what you would expect, but it's not quite there with 100 rolls. Let's see what happens if we have a lot more rolls. All right, here I have 1,571 rolls of the dice, and you can see that things are looking a lot better now. The real frequencies are quite close to the expected frequencies. If I did 10,000 rolls, it would be even better.